Okay, guys, welcome. So today we're going to talk about homogeneous linear ODEs, this time with constant coefficients. And again, I just want to stress here that these are second order linear ODEs with constant coefficients. So specifically the type of equation that we're now going to look at is where you have y double prime plus a times y prime plus b times y equal to 0. So again, we're looking at the homogeneous version of this, where a and b are now just constants. Okay, so one thing that I want to sort of refresh your memory on is that when we sort of had a similar situation in the first order case, if we had something like y prime plus ky is equal to 0, then we could use separation of variables to show that a solution is y equals some arbitrary constant times e to the negative kx. So sort of the idea is we're going to assume that our solution is of the form y equals e to the lambda x. So of course, now when you differentiate an exponential, what's going to happen is that you are going to essentially copy and paste what you started with, and then you're going to multiply by the derivative of the exponent. So in that case, y prime will just be a lambda times e to the lambda x, and your y double prime would be a lambda squared times e to the lambda x. So now, of course, when you substitute this in to your ODE, sort of in slow motion, what's happening here, I'll do this off to the side, is that if you're looking at y double prime plus a y prime plus b times y equals 0, well, then you get a lambda squared e to the lambda x plus a times lambda e to the lambda x, and then plus b times e to the lambda x. So now, of course, what you can do is factor out that e to the lambda x, and what you're left with is this second degree polynomial here, this lambda squared plus a lambda plus b. Okay, so now, of course, e to the lambda x is never equal to 0, right? Not without taking limits anyway. So what that then reduces to is that we want to look for roots of this polynomial here. And if we find a lambda that solves when that polynomial is equal to 0, then we have that y to that particular, or sorry, y equals e to that particular lambda times x will solve the original ODE. Now, of course, you can find solutions to the characteristic equation anytime by using the quadratic formula. Now, I know this is sort of odd to look at because your A's and your B's are a little bit out of place here, but this is exactly the quadratic formula. Now, of course, if you can get away with using something like factoring, or if you choose to go like completing the square, that's also another option. But this is just saying that you can always find solutions to that characteristic equation, right? So now, of course, you can use the discriminant, which is just a fancy way of saying that stuff inside the square root, to determine what kind of characteristic values you're going to have. So, of course, if that discriminant is positive, then you're going to get two real and distinct characteristic or eigenvalues, right? If your discriminant is equal to 0, that's when you get the real double root case. And if that discriminant is negative, that's when you get your complex conjugate values there. Okay, so I want to go through and do a bunch of examples of this, and we'll sort of see this in action. So up to this point, we've only been given, for this particular example, we're going to look at y double prime minus y is equal to 0, and we want to show that it has the solution y equals c1 times e to the x plus c2 times e to the negative x. So now up to this point, we've only been working with second order ODEs sort of by being given a solution, and then from that point being able to either get the other solution or we're just given both solutions and we verify that they work. So now we can actually solve this systematically. So again, so the idea is, and again, just note that this is the form y double prime plus a y prime plus b times y equals 0. We just have a equals 0 in this case and b equal -1. So this is a second order linear ODE with constant coefficients. Okay, so again, what do? We're going to assume that e to the lambda x solves the ODE. So then we get that y is equal to e to the lambda x, y prime, which we won't need in this case, is lambda e to the lambda x, and y double prime is lambda squared times e to the lambda x. Okay, so now plugging this into our ODE, we're going to get lambda squared e to the lambda x minus e to the lambda x is equal to 0. So once we factor out e to the lambda x, we're going to get lambda squared minus 1 is equal to 0. So now, of course, this part right here is really what we care about solving for. So we get lambda squared minus 1 is equal to 0. So again, you could use your quadratic formula here, but of course this will factor nicely. We could say this is lambda plus 1 times lambda minus 1 is equal to 0. So we get that lambda is equal to -1 and lambda is equal to +1. We'll solve this ODE. So now what does that mean? That means that our solutions are y equal, remember, we assumed that e to the lambda x was a solution, so we found that 1 lambda is -1, so we get y is equal to -x, and then of course the other one is e to just the positive x. So of course, since these are both solutions, we can use our superposition principle, and we can say that we have c1 e to the x plus c2 e to the minus x. And of course, this is the general solution. Okay, so that's how we can systematically solve that ODE there, right? Okay, so let's look at another one. So for this one, and again, this might be a good place to pause and try this on your own, since this is really not too difficult. This time we have an initial value problem as well, so we can take this actually one step further. So again, we're going to assume that y is equal to e to the lambda x as a solution. So if we plug all this in and factor, we're going to get lambda squared plus lambda minus 2 times e to the lambda x is equal to 0. So of course, this part here, again, if you can factor it, that's the way to go. And of course, in this case, we can. So this would be a lambda plus 2, lambda minus 1, and this is still e to the lambda x is equal to 0. So this one will give us that lambda is -2, and the other one will give us that lambda is equal to 1. So from there, we can conclude that our general solution again is going to be y of x is equal to, again, by the principle of superposition, c1 times e to the -2x, and then plus c2 e to the x. So that's our general solution. And now we can use the initial values or the initial conditions to get the particular solution. So if y of 0 is 4, that means that 4 is equal to just C1 plus C2, right? Because each of those exponentials will just become 1s once we plug in a 0. So we can't explicitly get C1 and C2 yet, but once we use our second condition, then we'll have a system that we can solve. So our second condition is y prime of 0 is equal to -5. So of course we need y prime, which would be a -2 C1 e to the minus 2x, and then plus C2 e to the x. So now if we combine this with our initial condition and plug in, we're going to get that -5 is equal to, it looks like a -2 C1, and then plus C2. Right? So now we can solve this system, right? For example, if we do the first one, so if we subtract the 2, let's just put it that way, then we'll get 9 is equal to 3 C1, which of course means that C1 is equal to 3. And if we do 2 times the first one and add it to the second, then that's going to give us what? So we'll have an 8 plus a -5, so that's a 3. And then our C1s will cancel. And then we'll get a 2C1 plus C, or sorry, 2C2 plus C2, so we get a 3C2. So we get that C2 is equal to 1. And therefore, we can say that our particular solution has to be y of x is equal to C1, which is 3 e to the minus 2x, plus C2, which is 1, so we could just say plus e to the x. And that's our particular solution. Okay, so hopefully this is not too difficult. Now, in the double root case, the derivation is a little bit different. It's not as straightforward, right? Because now, once we say that, now again, if you get the double root, that means that your discriminant is equal to 0. And you can always show that the actual eigenvalue will then be -a/2, right? So then that's going to give you that e to the -a/2 times x is a solution, which we're going to call y1. So y1 is equal to e to the minus a/2 times x. Now, of course, we couldn't just say, we can't use y2 equal to the same thing, because then we don't have linearly independent set of solutions, right? So the whole idea is we need to come up with a second solution that's independent, linearly independent to the first one. So the way that we're going to do that is we're going to find that using the reduction of order method. So we're going to assume that y2 is equal to some function of xu times y1, and then we'll use our derivatives and our product rules to arrive at this equation here. And of course, we know that since y1 is a solution, that this part will just zero out. And we can also show that this is going to be 0 in this particular case, because if I take the derivative of y1 times 2, right, the 1/2 and the 2 will cancel each other out, and I'll be left with -a. And this is just -a times y1. So if I find this sum here, that will also zero out. So now, of course, I'm just left with u double prime times y1 is equal to 0. And we know that y1, since again, y1 is e to the minus a/2x, which is never equal to 0, we can then conclude that u double prime has to be 0. And then if you integrate twice, you're going to get that u is equal to a constant times x plus another constant. So now, of course, we can we can choose this in such a way that we do not get proportional solutions. And of course, the way to do that is to make sure that C1 is non-zero and make sure that C2 is 0, right? So really C2 could be anything as long as C1 is non-zero, but to make it easier on ourselves, we're going to let C1 be 1, C2 be 0. So that way we get that we can choose U to be X and Y2 is just X times Y1. So in the double root case, what you're going to get is the usual one that you think of. You're going to get the e to the minus a over 2x, which is found by the root of the characteristic equation. And the other one will be similar, except you're also just going to multiply by an x in there, right? So it's the same thing, except we also multiply by a factor of x. Now, of course, you don't have to do this every time. Just know that in the double root scenario, this is the solution form. So as an example, again, this y double prime plus 6y prime plus 9y is equal to 0 has the form that we're looking for. So we, again, assume y is equal to e to the lambda x. So once we plug this in and factor, we'll get a lambda squared plus 6 lambda plus 9 times e to the lambda x is equal to 0. So if we factor this, this will become a lambda plus 3 squared times e to the lambda x, which tells us that we get a double root of lambda equal -3. So what does this tell you? This tells you that your general solution, again, since it's a double root, we get that our general solution is y of x is equal to arbitrary constant times just e to the -3x, and that the second solution is C2 times x of e to the -3x. And then that's our general solution. And again, just to quick verify that these two are linearly independent, if you find e to the -3x over x to the e to the -3x, of course, that's 1 over x, which is not constant. And of course, if you have chosen your x term to be 0, then of course you would have a constant. Again, that's trouble. So this is sort of the easiest way that we can sort of verify that. Okay, let's do another example. And again, this time with an initial value problem. So in this case, once I plug in my assumed solution and factor, we're going to get a lambda squared plus lambda plus 0.25 times e to the lambda x equals 0. Now, this one, when we factor, we'll get a lambda plus 1/2 squared, right? Because if you square 1/2, you'll get 1/4, which is 0.25, and if you add 1/2 and 1/2, you do get 1. And then times e to the lambda x equals 0. So that tells us that lambda is minus 1/2. So the general solution is y of x is equal to C1 times e to the negative x over 2. And our other one is the same thing, except just tack an x in front of it. So that's a general solution. So again, we'll use our initial conditions to get the particular solution. If y of 0 is 3, that means that 3 is equal to, and I guess we'll get a C1. And then the second term actually drops out because of the x in front of the e to the negative x over 2. So we get right away that 3 is C1. And of course, in the next condition, y prime of 0 equals -3.5, we would need y prime, which is a negative C1 over 2 times e to the negative x over 2. And then the next one, we would actually need product rule. So we'll have a C2. And then if I take the derivative of x, I have an e to the negative x over 2. And if I, right, and then times 1. And then I have an x times negative 1/2 e to the negative x over 2. Now, of course, we can use the fact that C1 is actually 3, and we can clean this up a little bit. So it looks like we're going to get a negative 3 over 2 plus C2 times e to the negative x over 2 plus negative x over 2 e to the negative x over 2. So now combining this with the initial condition, it looks like we're going to get negative 3.5 is equal to, it looks like just negative 3 over 2 plus C2. So from there, we can add the 3 over 2 to both sides, which is like adding 1.5. And then we get that C2 is equal to negative 2. So then our particular solution is going to be y of x is equal to C1, which we found to be 3, e to the minus x over 2, and then minus a 2 e to the, oops, sneak an x in there. So let's just rewrite it so it's a little more clear. So we get a minus 2x e to the minus x over 2. And there's our particular solution there. Okay, so we just have one more case to discuss in this video, and that's the idea of what happens when you have two complex roots. Now, if you haven't had a complex analysis class, this might take a couple of read-throughs to sort of see why we need the solution form that we need, but it's not hard to verify even if you've never had a complex analysis class. Okay, so the idea is now that, so I'm basically just using this omega here just as a placeholder so that I can sort of write the general form in a nicer way, right? So this omega is basically just sort of the complex part of your solution, right? So we can say that our two eigenvalues are negative a over 2 plus or minus I omega, right? So two solutions of this are when you have y1 equal to sort of the real part of the eigenvalue as the exponent of e times x, and then you have cosine of the imaginary part times x. And then we can have a similar solution type with just sine of the imaginary part. So then that gives us that the general solution is y equals to, again, exponent of the real part of the eigenvalue times x, and then we get this sum of cosine and sine terms with arbitrary constants. Now, I want to show you sort of why this happens. And again, if you've never had a complex analysis class, this may take a little bit of time to digest, but again, it's still not that difficult. So we're going to assume that z is a complex variable, meaning that it's made up of a real part r and an imaginary part t. So then you can use properties of exponents to write e to the z as e to the r plus it just by direct substitution. And then you can break that up using exponent rules. And now the claim here is that this cosine of t plus cosine of t plus I sine of t is the same thing as e to the it. Now, I'm not going to go through it here, but the idea is that you can show this pretty easily using a Maclaurin series for e to the x, right? So your Maclaurin series is e to the w is equal to like 1 plus w squared over 2 factorial plus w to the third over 3 factorial and so on and so forth. Now, if you replace w with I times t, what's going to happen is that all of your odd-powered terms are going to pick up an I, and in all your even terms, you're just going to get plus or minus 1, right? And then furthermore, in your odd terms, you'll get plus or minus I. So what's happening there is you're essentially getting your cosine and sine things to fall out, except all of your sine terms will have an I out front. So that's essentially what's happening when you can, and again, it's not a bad exercise to verify that e to the it does in fact give you this, but that's sort of the idea behind it. So essentially what we're saying here is that if our two eigenvalues are given by sort of these complex conjugates, then if I take e to the first eigenvalue, which is just the plus version of this, then what's going to happen is that by exponents, I can say that I have e to the negative a over 2x. That's not an issue. And then the e to the I omega x is like that e to the it, except just replace t with omega x, and that's what your cosine and sine terms look like. And then similarly in the subtraction version, we're going to get the same thing, except we get a minus in between for those sine terms. All right. Now, if you take these two forms and you add them and divide by 2, you get that one solution is e to the negative a over 2x times the cosine of the imaginary part times x. And then, of course, if you take the difference of the two and then divide by 2i, you get that another solution form is e to the real part times x times sine of the imaginary part times x. So then, therefore, your general solution looks like something like this, where, again, a and b are just constants. All right. And again, the idea here is that you don't have to do this every time. Once you find your imaginary eigenvalues, you can just go right to this sort of this general form. All right. So let's go ahead and we'll do an example. Okay. So it looks like I have most of this one written out already. So that's good. So in this example, and I guess I did that because it was annoying to factor. Okay. But the idea is, again, same idea. We want to assume that y is equal to e to the lambda x is a solution. So then our characteristic equation will look like this. And if you were to use the quadratic formula, you could find that your two eigenvalues are negative 0.2 plus or minus 3i. So again, what happens there? Your negative 0.2 is the real part. So that's becoming your exponent of e times x, of course. And the imaginary part being 3 is going to become the inside of these sines and cosine functions, of course, each of them times x. And then the a and b are the arbitrary constants. So if I use the initial condition that y of 0 is 0, of course, the e term will just become a 1. And cosine of 0 is 1, but sine of 0 is 0. So this is going to go away. And this will right away give you that a is equal to 0. So, of course, we can use that to our advantage when we find the derivative, because then we have to do it one last time, of course. Now, the derivative by the product rule will be this mess of stuff right here. And again, we now just use the initial condition that y prime of 0 is equal to 3. And we can conclude from that that b is equal to 1. So then our particular solution in this case is, since a is 0, there's no cosine term. Right, that drops out. And b is equal to 1 just means that you only end up with the sine term. So this is your particular solution. Okay, one more example. And then we'll summarize this, and then we'll conclude this video. So the one more example, and again, this is actually a pretty quick one, is that if we have y double prime plus omega squared times y is equal to 0, then your characteristic equation looks like this. And then, of course, that indicates right away that your lambda 1 and your lambda 2 are just purely imaginary. It's plus or minus I times W. So that tells you, since your real part is, you don't see it, this is no real part. So you just get e to the 0, which is 1, so that's essentially going to go away. And in this case, your imaginary part is omega, so you're going to explicitly get this as your general solution. Okay, now to summarize everything, in the two real cases, you essentially just take your two eigenvalues as your exponents of e, and you multiply them by x, and you call it a day. For the double root case, it's a little bit more interesting, but you have the e to the double root, which is negative a over 2, and you have one multiplied by an arbitrary constant, and the other one is arbitrary constant times x. For the complex conjugate case, what happens is that you get e to the real part times x, and then this sum of sine and cosine terms of the imaginary part. Okay, so that concludes this video on second order linear ODEs with constant coefficients. Hope you enjoyed, and I will see you next time.